video, you will define composite function, understand the principle behind composite function, and solve for composite function. For composite function to make sense to you, we require that you understand well operations of functions. Among others, the rules we follow when we are adding, subtracting, multiplying, dividing polynomials, and laws of exponent. So what is composite function? Let G is a function from A to B, and F be a function from B to C. The composite function f circle G is a function from A to C defined by f circle G of A is equal to f of G of A for all A element of A. The formal way of reading this notation for composite function is f circle G. Some books read it as f of G. Now, let's go back and understand the definition of a composite function. Based upon its definition, when we talk about composite function, we are dealing with two functions. The first function is denoted by G, where capital letter A represents its set of inputs or domain, while capital letter B represents its set of possible outputs or codomain. We learned that small letter A and small letter B represent every member or element of domain and codomain respectively. The second function is represented by F. The capital letter B is its domain and the capital letter C is its codomain. From this illustration, it looks like the codomain of G, which is B, is the domain of F, right? This is because of the principle behind composite function. As another way of combining functions, it uses the codomain or set of outputs of the first function as the set of inputs or domain for the second function. This technique is done to get the composite of two functions. To sum it up, a composite function denoted by f circle G is a function from A to C. Here, A, the input of the composite function, is the output of function 1 or G. And C is the set of outputs of our composite function we will obtain after we plug in A to function 2 or F. Let's understand further composite functions using examples. Suppose we have f of x equals 2x plus 1 and g of x equals 5x minus 1. Let's find f circle g of x and g circle f of x. Let's first solve for f circle g of x. This notation means that finding f circle g is finding the f of g of x. To do that, we need to input the equation of g of x in the equation of f of x, or we can simply say we will replace all x variables in the equation of f by the equation of g of x. Since the equation of f of x is 2x plus 1, by substituting 5x minus 1, we will have 2 multiplied by the quantity 5x minus 1 plus 1. To simplify this, we will apply the Pemdas rule, working from left to right and considering the order of precedence. By distributive property of multiplication, we will multiply each term inside the parenthesis by 2. Therefore, 2 multiplied by 5x will give us 10x. Then, 2 multiplied by negative 1 is negative 2, then plus 1. Since negative 2 and 1 are like terms, we will combine them. They will give us negative 1. Therefore, f circle g of x is 10x minus 1. We will do the same procedure for the second composite function, which is g circle f of x. G of f of x will give us g of quantity 2x plus 1, which means we need to substitute this to all x variables in the equation of f of x, which is 5x minus 1. Therefore, we will have 5 multiplied by the quantity 2x plus 1 minus 1. Applying the Pemdas rule and distributive property of multiplication, 5 multiplied by 2x will give us 10x. And 5 multiplied by 1 will give us 5. Therefore, we now have 10x plus 5 minus 1. By simplification and combining like terms, we have 5 minus 1. Therefore, g circle f of x is 10x plus 4. To sum it up, the composite function f circle g of x is 10x minus 1, while g circle f is 10x plus 4. Here's another example for you. Here, we will determine the composite function of f of x and g of x. The first thing we will do is to find the f of g of x. To do this, we will substitute the equation of g of x, square root of 3x plus 2, to the x variable of the equation of f of x. This procedure will result to 2 multiplied by quantity square root of 3x plus 2 squared plus 1. Applying Pemdas rule, we know that the simplification of the radical sign and the exponent will lead to quantity 3x plus 2 raised to 1 plus 1. Applying distributive property of multiplication, we will multiply 3x by 2 and 2 by 2. They will give us 6x plus 4 plus 1. Then, adding 4 and 1 will lead to our final answer, which is 6x plus 5. Maybe some of you are perplexed on why quantity square root of 3x plus 2 squared became 3x plus 2. This can be explained by the law of fractional exponent that states that the nth root of quantity x raised to m can also be written as quantity x raised to m over n. The rest of the procedures are simplifications. Let's have the next example. In this problem, we need to find two composite functions f circle g of x and g circle f of x using the given functions such as f of x equals 5x minus 3 and g of x equals x plus 3 all over 5. Let's start with the first composite function denoted by f circle g of x. I will replace the g of x by its equation x plus 3 all over 5. Now, f of x equals x plus 3 all over 5 means that we need to substitute it to each x variable in the equation of f of x. There is only one x in the equation, therefore we will have 5 multiplied by the quantity x plus 3 all over 5 minus 3. Now, if we multiply 5 by x plus 3 all over 5, 5 and 5 will be equal to 1. Since 5 divided by 5 is 1, we are left with x plus 3, then minus 3. Now, combining like terms, positive 3 and negative 3 will give us 0. Therefore, f circle g of x is equal to x. One of the explanations why 5 multiplied by x plus 3 all over 5 became x plus 3 is because we are multiplying two fractions here. 5 over 1 and x plus 3 all over 5. It is 5 over 1 because it is a rational number. A rational number is any number which we can express as a quotient or a fraction of two integers a and b, where b should not be equal to 0. When a is 0, b should not be equal to 0. Why not equal to 0? Because the fraction will lead to an unreal or undefined value, which is not a part of the real number system. Since we are multiplying two fractions, we will apply the rule numerator to numerator, denominator to denominator. Therefore, we will have 5 multiplied by quantity x plus 3, then 1 multiplied by 5 will give us 5. Here, 5 over 5 means that we are dividing 5 by 5, which will give us 1. Therefore, we have x plus 3. Applying the definition of rational numbers, x plus 3 can also be written as x plus 3 all over 1. Let's now find g circle f of x. Similar to the previous examples, we need to plug in the equation of f of x, which is 5x minus 3, to the equation of g of x, which is x plus 3 all over 5. Substituting 5x minus 3 to the equation, we will have quantity 5x minus 3 plus 3 all over 5. Now, the simplification of our equation requires us to add negative 3 and positive 3, which will give us 0. Therefore, we will have 5x over 5. Simplifying 5x over 5 will give us x. Therefore, g circle f is equal to x. Are you also curious why F circle G and G circle F are both x? In this example, we need to find G circle F of 7 and F circle G of -1 using F of x equals 2x plus 1 and G of x equals square root of x plus 1. We will show you two methods to solve this problem. Let's first solve for G circle F of 7. Let's apply the illustration we presented at the beginning of this video. Using the composite function principle, to solve for G circle F of 7, the first step is to find for the value of F of 7. To do this, we will plug the input or domain 7 to the equation of f of x. After this, the value of f of 7 will be our input for the second function g of x to find g circle of 7. Let's do the first step. Let's find f of 7. To do this, we need to substitute 7 to the x variable of the equation of f of x. Therefore, we will have 2 multiplied by the quantity 7 plus 1. Multiplying 7 by 2, we will get 14 plus 1. Then, adding 14 and 1 will give us 15. Therefore, the value of f of 7 is 15. Now, in step 2, we will use 15 as the input for the second equation g of x to solve for the value of g of 15, which is also the value of g circle f of 7. Let's perform the step 2. Let's find g circle f of 7 by solving for g of 15. As instructed, we need to plug 15 to the equation of g of x, which is square root of x plus 1. We will have square root of 15 plus 1. Let's simplify the terms under the radical sign. 15 plus 1 is 16. Then, square root of 16 is positive -4. Therefore, g circle f of 7 is positive -4. As a wrap-up, here's the procedure we did to solve for the composite function g circle of f of 7. Here's another method of solving for g circle f of 7. This method requires us to find g circle f of x by substituting f of x to g of x. By substituting 2x plus 1 to g of x, we will have square root of quantity 2x plus 1 plus 1. Since 1 and 1 are like terms, we can combine them. That should give us 2. Therefore, our equation now is square root of 2x plus 2, which we can also rewrite as square root of 2 multiplied by x plus 1, since the common factor of 2x and 2 is 2. Now that we have g circle f of x, we will use its equation to find for g circle f of 7 in step 2. This is done by substituting 7 to our g circle f of x. Substituting 7 to x, we will have square root of 2 multiplied by 7 plus 1. Applying the Pemdas rule, 7 plus 1 is 8. Now we have square root of 2 multiplied by 8. Then we have square root of 16, which is positive negative 4. Therefore, g circle f of 7 is positive negative 4. Please take note that you are free to choose and use any method which you think is easier for you. To find f circle g of negative 1, we will follow the same procedure in f circle g of 7. We will first solve for f circle g of x by plugging in the g of x to f of x. Now, I will replace x variable in 2x plus 1 by square root of x plus 1, which will give us 2 multiplied by the quantity square root of x plus 1 plus 1. 2 multiplied by quantity square root of x plus 1 will give us 2 square root of x plus 1 plus 1. Since this is now the simplified form of our equation, f circle g of x is 2 square root of x plus 1 plus 1. We will use the equation of f of g of x to find f circle g of negative 1. We will substitute negative 1 to the x variable of the f of g of x. This will give us 2 square root of quantity negative 1 plus 1 plus 1. Applying Pemdas, we will simplify first the operation under the radical sign. Therefore, negative 1 plus 1 will give us 0. Then, the square root of 0 is 0. Now, we have 2 multiplied by 0 plus 1, which will give us 0 plus 1. Therefore, f circle g of negative 1 is 1. Did you find this video helpful? For more SEEKnaYan videos, please subscribe to my channel by clicking the subscribe button below and activating the notification bell. I'll see you all again in the next episode of SEEKnaYan. Problema sa sipnayan, isik mo na yan kay Migo Mendoza.